I'm Xinyi Zhang from Peking University and Alibaba Cloud. Today, I'm very pleased to introduce our latest work, ResTune, a results-oriented tuning system boosted by meta-learning for cloud databases. Cloud databases, such as RDS MyCircle, have hundreds of knobs. Usually, DBAs are responsible for tuning those knobs based on their experience. However, manual tuning cannot scale to different workloads and various instances on the cloud. Automatic knobs tuning becomes important for the cloud providers. The knobs configuration affects the performance of database, and also they determine the resource usage, such as CPU, memory, and I/O. Optimizing the resource usage is beneficial. It could reduce the total cost of ownership, avoid the privation, and ensure the availability for end users. However, existing auto-tuner methods have limitations. First, all of the methods only focus on improving the performance. They not consider optimizing the resource usage. Second, search-based methods do not take advantage of past trials. It's inefficient compared to model-based methods. Third, reinforcement learning-based methods usually take thousands of iterations to find ideal configuration. The tuning overhead is high. Finally, Bayesian optimization-based methods are proved to be successful for tuning the performance, but existing work using Bayesian optimization methods has vague adaptability with different hardwares and workloads on the cloud. We summarize our goal in this slide. First, we want to consider optimizing the performance and the resource usage at the same time. Second, we want to boost the tuning process with different path tuning tests from various instance types and workloads on the cloud. Here we show the throughput and CPU usage on a real workload with two controlling knobs. We found that the throughput of real workload is often bounded by the client-side request rate. The request rate is around 11,000 in this example and does not necessarily reach the processing capacity of database. For the common application scenarios, squeezing more throughput from the capacity is not the goal. Second, there are opportunities for us to optimize resource utilization without sacrificing the performance. Since we can observe from this figure that a wide range of configurations have similar throughput, but with different CPU usages. Therefore, we could find knobs with optimized resource utilization in the feasible area where the throughput is acceptable. We formalize the results-oriented tuning problem in this slide. We define it as an optimization problem with constraints. We loosen the performance goal to satisfy the SLA in the constraints. The constraints are defined by the throughput and latency and their default configuration, since we assume the configuration before tuning satisfies the SLA. We use the extended Bayesian optimization to solve the problem. In traditional Bayesian optimization, it uses acquisition functions to get the search of optima. In this one-dimensional example, we want to minimize the resource usage while keeping the SLA positive. The algorithm always evaluates the candidates with the largest acquisition function value, as the green line shows. We can see the method keeps trying the invisible knobs with minimal CPU utilization, but unfortunately, it keeps violating our positive SLA requirements. In other words, directly applying the acquisition function leads to invisible knobs recommendations. Our challenge is how to minimize the resource usage without sacrificing the SLA. The basic idea is to estimate the probability of feasible knobs using Gaussian process. In ResTune, we use acquisition function, which is the original expected improvement function, multiply the probability of satisfying the SLA. Let's look at or solution for the previous problem. The main difference is the acquisition function, the green line, gets the search in the feasible area. The method found the best feasible knobs within 10 iterations. Our second goal is to use prior knowledge in past tuning tasks. The iteration is to capture the shared information among different tuning tasks from various instances and workloads on the cloud. ResTune is highly motivated by the meta-learning. With every task learned, optimizing new tasks becomes easier, requires fewer examples, and less trial and error. In our framework, the prior knowledge is extracted from historical tuning tasks by ensemble. Each tuning task can be represented by a Gaussian process, also called a base learner. The base learner models the relationship between the knobs and the database metrics, such as resource usage. If a historical task J is similar with a new task, its base learner will be more likely to transfer well to the new task. Summing up all the predictions weighted by the task similarity, we can build an ensemble Gaussian process, which is defined as our meta-learner. The key challenge is how to determine base learner's weight. We propose two strategies. The first is learning from meta feature. It's used for initialization when we have little observations of the target task. The second is learning from model predictions. It's used after the initialization, which also avoids overfitting to the historical tasks. Learning from meta features determines the weights by measurable properties of tasks. ResTune learns the properties by workload characterization pipeline. The pipeline uses the SQL statements as input and output a resource usage level predicted by a random forest model. Now we can calculate the static weight by computing the distance between meta features from target task MT and historical tasks. When we have several observations of the target workload, ResTune switches to learning from model predictions. We define base learner similarity in terms of how accuracy base learner can predict the performance of the target task. The challenge is that the performance can differ in scale significantly among various hardware environments on the cloud. The figures below can be a good example. The two plots have very similar response surfaces in shape, but instance A's actual value of throughput are much larger than B's. Using existing workload mapping strategy, we cannot transfer the shared knowledge between the two hardwares. Since we only need to identify the location of the optimal, we found that the actual value of the predictions do not matter. Therefore, we define the weight by the ranking loss of base learners against the target observations. Let's look at the example when we have 4 target observations. The target ranking is configuration A's throughput is larger than B's, B is larger than C and D's. One of the base learner, G, its ranking is BDAC. The ranking has 6 misranking pairs. Then the ranking loss for J is 1/2. For the target workload, we evaluate target base learner's ranking loss in leave one out setting. Finally, each base learner is weighted with the probability that it has the lowest ranking loss among all the base learners. With the 2 weight assignment strategies, ResTune utilizes tuning experience adaptively. During utilization, it's a common practice to boost track optimization by sampling. However, we realize that the meta features generated by workload characterization can give a basic understanding about task properties. Therefore, using the static weight, the meta-learner can suggest knobs that are promising according to similar historical tasks. The dynamic weight measures the similarity of tasks in the optimization problem. As the right figure shows, the historical base learners weight W1, W2, W3 strings, thus avoid overfitting. This is the architecture of ResTune. When a tuning task is launched, a copy instance of target DBMS is made, and a time window of the target workload is collected for future replay. The copy instance is deployed in the user's environment to protect data privacy. Two main parts of ResTune are deployed separately: ResTune client and ResTune server. ResTune client consists of metadata processing component and the target workload replay component, and is deployed in the user's environment. It handles the pre-processing of target tasks and the evaluation of suggested knobs. ResTune server is responsible for recommending the knobs for each iteration and is deployed in the backend tuning cluster, consisting of two components: knowledge extraction and knobs recommendation. After processing the target task in ResTune client, the meta feature and the target-based model are sent to the knowledge extraction component of the ResTune server. ResTune server then calculates the static weights and the dynamic weights based on the client's input. Meta feature and base model stores in the data repo. After assembling, a meta learner is used to recommend new configurations. Finally, the knobs are applied to the database, and the replayer is triggered. Then the evaluation results are appended in the observation of the target task, fine-tune, and iteration. When the tuning task ends, the metadata of the task is also collected to the data repo. In the experiments, we use MyCircle in 6 different hardware instances. We use 3 benchmark workloads and 2 real-world workloads in production. For data repo, we collect metadata from 34 path tuning tasks on instance A and B. To prove the performance of our ResTune, we compare with other file methods. Since none of the existing auto-tuner optimize resource usage, we carefully modify them to solve the results-oriented tuning problem defined in this paper. Default is the default knobs provided by the experiment DBA. iTuned uses Bayesian optimization methods without using path tuning data. We change its objective to minimize the resource usage. Auto-tune with constraint is another Bayesian optimization-based method using historical tuning data by workload mapping. We replace auto-tune's acquisition function to our extended acquisition function to get search in the feasible region. CDP2 with constraint is a reinforcement learning-based method. We modify its reward function to encourage the agent to minimize resource usage and satisfy the SLA. And then it's ResTune without meta-learning to show the benefit of our meta-learning design. Now we evaluate the tuning efficiency of ResTune using all the data in the data repo without leaving out the target workload. The figure shows the CPU utilization of the best feasible knobs. As shown, ResTune can reduce the default CPU usage and guarantees the SLA. Besides, we can see ResTune, even without meta-learning, can perform much better than iTuned and CDP2 with constraint. The 3 methods do not use historical tuning data. The main reason is that iTuned uses simple Bayesian optimization without considering SLA constraints. It tends to recommend infeasible configurations. CDP2 with constraints learns the mapping from internal metric to the configurations. However, given a target workload, the optimal configuration is the same for any internal metrics, leading to the fact that the action and the state are not necessarily related. Therefore, such modeling complicates the problem, since the training overhead for CDP2 is relatively high. And with our meta-learning design, ResTune achieves large speed up than auto-tune with constraints. As there are various instances and workloads on the cloud, it's vital whether our ResTune can adapt to those changes. We evaluate hardware adaptation in 3 settings, using data collected on instance A to tune instance B and B to A, and using all the data collected on AB to tune instance C, D, E, F, respectively. For workload adaptation, we hold out the tagged workload data from the data repo. The figure shows the results. When transferring between 2 instances and transferring between workloads, we can see ResTune has better improvement and faster speed than the other baselines. Auto-tune with constraints uses absolute or actual value for calculating the similarity and does not with the target and historical data. Therefore, it fails behind ResTune more in the adapting setting. The table shows the results when transferring the base learners trained on instance A and B to more hardware instances. The red square shows the speed up due to augmented learning. Then we evaluate the performance of ResTune and optimizing the I/O and the memory. We conduct experience on instance E, tuning sysbench and TBCC under the workload adaptation setting. The main difference from optimizing CPU usage is that we change the objective to the I/O and memory, respectively. We can see ResTune reduces 87% of I/O and 69% of memory. Okay, that's my talk. Thanks. If you have any questions, welcome to asking.